Are people familiar with the term chromatography? Is this a new word for folks, or have you heard it before?
New for me.
Mm-hmm.
It's new for me too.
Same. Mm-hmm.
Yeah, I'm not terribly surprised. It's a fairly standard lab technique to use, but probably not so much in high schools and other sort of introductory chemistry classes. But as you go further along, particularly if you're going to be taking organic chemistry or in particular biochemistry or molecular biology, chromatography is like super important. I've been doing chromatography for about 30 years now. And basically, anyone know what chroma means?
It's something related to color.
That's right. Very good. Yeah, color. It's a Greek word for color. So chromatography originally was sort of study of color and pigments, and it became to be known as the separation of colored pigments. And that's precisely what we're going to be doing today. Now, if we were together in the actual physical lab, the lab we would have been doing is paper chromatography of different metal ions. We would have been separating iron 3, iron 2, nickel 2, I think copper 2, and just looking at them separating on a piece of paper, and then looking at the colors that these different metals can take. And so what you're going to be doing today is actually looking at all the different colored pigments in different plant leaves. And so what we're going to do is like basically a virtual extraction. Can someone tell me what extraction means?
Like
taking something out.
Yeah, basically it's the separation of liquids from a solid, generally speaking. So what we'll do is we'll take these sort of spinach leaves, other sort of colored leaves. I think we're going to be looking some really pretty colors from leaves taken from the fall, just before they fall off the trees. You know, they take on these beautiful yellow and orange and red colors, and you extract them with a solvent. And so these colors, these pigments, are bound up in the solid. And what you do is you take a solvent, like an organic solvent, something like a methanol or ether or ethanol, and you mix it with the solid. And what it does is it strips these pigments out and puts them in solution. That's the critical thing when you're making an extract. You want to make solvent means you're going to be dissolving something into it. And so we're going to be dissolving something in this solution so that it goes from being a solid and then dissolving it into liquid. And so there's two what we call phases in doing chromatography. Anyone remember what the two phases are?
Caton and
Stationary and mobile.
Yeah, right. Exactly. So what's the mobile phase? What does the mobile phase do? I mean, the word mobile kind of gives part of it away. there. So when we have our pigments, whatever it is we want to separate, how are we going to separate them? What will the stationary phase do, and what will the mobile phase do? Or another way, what is the stationary phase in this experiment?
We use gel or polymer.
It can be, yes. And you can use polymer. You're going to use a lot of different things. But in this particular experiment, what are we going to use as our stationary phase? It's kind of in the title.
Paper?
That's right, paper. So the paper is the stationary phase, and just like it says, it's stationary. It doesn't move. So what we're going to do is we're going to take our pigments that have been dissolved in a solvent, and we're going to put the paper into it. The paper is going to stay where it is. But what's the mobile phase going to do?
Move compounds.
It's going to move the compounds? Okay. How's it going to do that? Or how is it going to move? I'll just put it that way. How is the mobile phase actually going to move? What makes it move?
Mm.
Here, what I'm going to do is go to the oh, oops. We should have, oh, I should have opened, oh, here we go, lab manual. Screen. So can everyone see the screen now? So this is from your old, well, old. This is from the original lab manual. Shh, doggies. Man. Whenever they hear motorcycles, they go insane. So this is from the original lab manual that we were going to use if we were working in the lab. And so I made that available on Canvas as well. And so it's also paper chromatography and separation of compounds. And it shows you the mixture. So you're going to be taking a mixture of different things. And what the chromatography does is separate it into its different components. And so it shows you all the different types. So there's thin layer chromatography, which someone pointed out, if you want to use a polymer, generally thin layer has like a alumina gel or a silica gel, which will do the separation. There's liquid chromatography, paper chromatography. There's also, you can separate gases. You can take a mixture of gases and separate them. And so what the chromatography actually does, get it down here, is that the liquid phase, and I'll get see if I can draw on this. So the liquid phase is actually the solvent that you're going to be dissolving the different components in. And that's right here. So at the bottom, we've got our solvent, all those different compounds dissolved in it. We put our piece of paper in it, and it's capillary action. Anyone know what capillary action is? Have you heard of capillary action before? basically the force that draws the solvent up the paper. You know what? So have you heard of capillary action before? I'll leave it like that. Have you heard of it before?
Nope.
I have.
Fair enough. No? Okay, fair enough. Just want to know what I'm dealing with. So capillary action is basically, it's the force that draws liquid like up. And so we know that water has an affinity for other molecules of water. And we'll talk a lot more about this later on in the class. But you know that water likes to bond to itself. Water is very sticky. It bonds to other water molecules. So if we have some water or other sorts of solvents that act like water, since it bonds to itself, some of the water is attracted to the paper. There's a certain, what we call affinity. Now, affinity just means it's attractive. It means that there's an attractive force between the two. So there's an affinity between the water and the paper. And so the water starts bonding with the paper, not chemical bonding, but sort of like an interaction with the paper. And it sort of sticks to the paper, and then it draws other water molecules up the paper. And I think the example that was given, someone must have left if you're taking a bath or something and a towel fell in the bathtub. You ever notice that the water moves up the towel and over the side of the tub and then starts leaking water on the floor? Has that ever happened to anybody? Yeah. I'm the only person who's left a towel in the bathtub, really?
Yeah, that's happened to me before.
Yeah, that's capillary action. And so the water molecules have a certain affinity for the cotton fibers in the towel. And so they start climbing up the towel. And the water molecules have an even higher affinity for each other. And so they pull more and more water molecules out of the tub and up the towel till they get all the way down. And then you start leaking that out the bottom. It's like a wick. Taking a wick in there and you're drawing up the water from the tub and then over the side. And the same thing's happening here. So basically you have water molecules or other solvent molecules pulling a column of solvent up the stationary phase. So the paper is the stationary phase. The water has a certain affinity for it. It bonds to it and moves, pulls more water up. And so, and so the longer we leave this paper, the longer we leave the paper in the water, the higher the solvent will move. And the solvent will just move up, 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 till it gets all the way up to the top. Now, the other thing that's going to be happening is that the mixture of molecules that we put in the solvent, whether they were metal ions like we were going to do in the lab, or in this instance, they're going to be things like chlorophyll and other colored pigments, they are going to have a certain affinity for the solvent. We know they have affinity for the solvent because the solvent dissolved them in the first place. And so they must have some sort of affinity for the solvent. They dissolved in it. But they will also have an affinity for the paper. And all we're doing here when we do chromatography is we're making a separation based on the relative affinity of these different molecules for A, the paper, and B, the solvent. And so if these pigments have a higher affinity, if they want to bond more to the solvent than the paper, are they going to go higher on the paper or lower? What do you think?
Higher.
Higher. They're going to move, exactly. They're going to move along with the solvent. So if they are chemically more like the solvent than they are the paper, they're going to move with the solvent and move up further up the paper. On the other hand, if they're chemically more like the paper than they are the solvent, are they going to move higher or move lower?
Lower.
Mm-hmm. They're going to move, they're not going to move much at all because they're going to spend their time stuck to the paper, meaning they have a higher affinity, more bonding to the paper than they do to the solvent. And so as the solvent moves up, they're going to leave these molecules behind. And so basically what we're doing is we're separating molecules based on their affinity for the solvent. If they have more affinity for the solvent, if they're more chemically like the solvent, they move higher. If they're more chemically like the solid phase or the stationary phase, in this case the paper, they're going to stay stuck to the paper. And so they're not going to move very far at all. And so that's basically, in a nutshell, how chromatography works. We're going to be looking at the relative affinity for the mobile phase and the stationary phase. So generally, you try and pick a stationary phase and a mobile phase that are different. So because if they were both the same, all the spots would basically move to the same place. They'd have the same affinity for the paper and the solvent, so they'd all move together. And so we wouldn't be able to separate them. So what we want is something different. We want the mobile phase to look different chemically than the paper does. So could anyone tell me if you've heard the terms hydrophilic and hydrophobic? Have you heard those terms before?
Yep.
Yes.
What do they mean to you?
Hydrophobic, isn't that when they are not attracted to water? And
Right.
hydrophilic is when they are.
Right, yeah, I mean, philic actually means likes, and phobic means doesn't like, or scared. And in chemistry, hydrophilic means something that's very soluble in water, something that dissolves easily in water and likes being in water, has a very high affinity for water. Hydrophobic means the opposite. It means hydrophobic things don't dissolve readily in water. They prefer something organic, like hexane or octane or something like that. Something with a long chain of carbons and hydrogens, hydrocarbons. It's very hydrophobic. Those things don't dissolve in water at all, like oil and water. Oil has long chains of carbons and hydrogens, and so it prefers being around other molecules that look like it, that have long chains of hydrogens and carbons. So generally, when we sort of do chromatography, we want one thing to be more hydrophilic, and we want the other thing to be more hydrophobic, and so we can separate those compounds based on that, okay? And so as the liquid moves up the paper, generally the liquid is going to be more hydrophobic than the paper. Paper is pretty hydrophilic. It has a lot of oxygen and nitrogen and elements that are generally soluble in water. We'll learn more about why that is a little bit later. And the solvent will be more hydrophobic. And so the solvent generally, as it moves up, will take more hydrophobic elements or hydrophobic compounds with it. And the more hydrophilic or water-loving compounds will stay stuck on the paper, okay? So let me go back. All right. Clear. So good. So this is the online lab. Can everyone read this? Everyone get the same view? The paper chromatography lab we're to be doing today. Does everyone see that now?
Yes.
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 Cool. So we're going to be performing a separation of the plant extracts. First, we're going to extract them, and then we're going to use chromatography to separate them. And we're going to figure out what it is that the stationary and the mobile phases are actually doing. And then what we're going to do is something called the retention factor. And it's the retention factor that will help us determine the differences between these different compounds. What does the retention factor mean? Anyone tell me, or how do we calculate the retention factor? Has no one read the
Distance of the spot divided by distance of the solvent front.
Right. So if you have a high number for retention factor, does it have a higher affinity for the solvent or a higher affinity for the paper?
The paper?
So remember, you take the distance it moved, right? And then divide that by the distance it moved up the paper divided by the distance that the solvent moved. So if it has a high number, was it moving with the solvent or was it staying stuck to the paper?
The solvent.
The solvent, right. Because if you have a compound that basically has no affinity for the paper at all and just likes being in the solvent, it prefers to be in the solvent, it's going to move with the solvent. And so when you divide the distance that molecule moved by the distance the solvent moved, it'll be 1 because it moved basically with the solvent. So the retention factor is a measure of how high the affinity was of that molecule for the solvent, because it's a measure of how much it moved with the solvent. If it has a high affinity for the solvent, it will move with it. If it has a very high affinity for the paper, it won't move very much. And so your retention factor will be low. So can everyone go to the site? Have people gone to the site already? You can just control click on it and it'll take you to the site. Let's go. All right, so you can see the computer screen now?
Yes.
Okay. So I sort of copied and pasted the theory in there already. So you can go over that. These are the different pigments that we're going to be looking at. Chlorophyll A, chlorophyll B, xanthophylls, and carotenoids. So you can see they're all sort of different, they're different colors. And so we could visualize them, we can see them. The chlorophyll A will be really dark green. Chlorophyll B will be a little more yellowy, but also sort of a yellow-green. Xanthophylls will be yellow. And carotenoids, you probably figured out, those are orange. A lot of them in carrots, where it gets its name. And so as they move up the paper, you'll actually be able to see them moving. In other sorts of chromatography, like the one we would have used in the lab, some of these things you can't see and you have to stain them with something else in order to visualize them. But these are already colored compounds, so we can see them very easily. And so let's go to the procedure. So if we were going to do this in the lab, these are basically the materials we would need. So we take leaves, we would put them in a mortar and pestle. You've probably seen like a mortar and pestle before, like you're making guacamole. Mortar and pestle is a good thing to use. You take the leaves, you put them in there, you grind them up, you add some solvent to it and grind, 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 grind. So what the grinding does is it breaks up the solids and allows access to the solvent to get in there and actually do the extraction. So as you're grinding it up, you're allowing more and more access to these molecules, to the solvent, and so then they dissolve in the solvent. Okay. Oops. So we're going to look at spinach leaves because they have a lot of chlorophyll in them, and we're also going to look at some, like I said, leaves taken from trees in the autumn. So you get these really, really pretty colors. So let's go to, so the animation, and you can watch that whenever you would like. It's basically shows you how it actually works in the lab. So what you would do is after you've made your extract, you put that in the bottom, go to the procedure again. You put that in the bottom of what we call a chromatography chamber. So here's our chromatography chamber here. So we put our solvent in the bottom. We drop our flat piece of paper in there, and we don't want it to touch the sides because we just want the solvent to go up the paper, not up the side of the chamber. And then just allow it to go up, up, up. And there's a top on it because some of these solvents are kind of nasty. Like here, we've got ether and acetone. You don't want to be smelling those. You get a really bad headache. And so they go up, move up the paper, and when they've got to a certain level, we take it out, and then we could like look at the paper itself, or we can photograph it, whatever we want to do. Is there a problem with letting the solvent go all the way to the top of the paper? Is there a reason why you would or would not want to do that? Should you let the solvent go all the way to the top of the paper? So if this is my paper and my solvent is moving up, let's say this is my solvent front here, and it's moving up the paper. Should I let it get all the way to the top of the paper?
No.
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 Yes, no? Okay. If yes, why? Why should you let it get all the way to the top? Someone said yes. Why do you think that's a good idea? I mean, in a way, I agree. I mean, you want it to go as far as possible so you can get as good a separation as possible. But should you let it go all the way to the top?
Because if it goes to the top, we will not be able to measure the.
Yeah, that's one very good reason. Yes, you don't want to go all the way to the top, because if it went all the way to the top, you wouldn't be sure if it went all the way to the top or did it keep going. Because eventually the solvent will get to the top, and then once it gets to the top, it evaporates, right? So it's a liquid. It's a liquid in the paper. It's a liquid, it's a liquid, it's a liquid. It gets to the top of the paper, and then it evaporates. And then it's replaced by more solvent as it moves up, and then it evaporates. So eventually, if you just left it for a really long time, all the solvent would go up the paper and evaporate. What would happen to the different molecules if you left it run for a really long time?
Dry.
It would dry, yes. But what would happen to the movement of the molecules? Would they keep moving too?
No.
It'll be equivalent.
Be equivalent. Yes, I think I know what you're talking about. Can you explain what you mean by that?
Well, they'll all go up at a certain time, but it's just some will go up slower than the other. But in the end, it'll just kind of meet up there. So just
Exactly. Exactly. Yeah, basically what you'd have is like an 8-car pileup at the top of the paper. They'd all keep moving. And so eventually they'd all move to the top, and there'd be no, basically what you would have done is taken the mixture, separated them, and then they'd all pile up at the top again. And so you would have basically unseparated them as they sort of piled up into each other. So you don't want the solvent to go all the way to the top. You want it to go far, but you don't want it to go all the way to the top. So if you were doing this experiment, you have to carefully watch it until it got to about maybe 80 or 90% of the way up the paper, and then stop it. Because then basically what you're doing is taking a snapshot of where all the pigments are at that point. That's about as far separated as you can get them. If you let them keep going, they're going to basically separate and then reassemble again. Okay. So the animation basically shows you how it really works, and you can see that yourselves whenever you'd like. So we're going to go to the simulator. So here, so is everyone on the simulator tab?
Yes.
Okay, good. So what we're going to do is so it asks you to select a pigment extract, and so there's a number of different ones. There's spinach, maple leaves in the spring and summer, or in the autumn and the winter, or fall foliage. There's a number of different ones. And then there's different solvents you can use. The first one is a mixture of ether and acetone. Ether is extremely hydrophobic. Ether is very hydrophobic. Acetone is somewhat, it has some hydrophilic properties and some hydrophobic properties, which is sort of what you want. You want your solvent to be both hydrophilic and hydrophobic, because you want it to be able to bond somewhat to the paper, or else it won't move up. But you want it also to be hydrophobic, and so the molecules, the more hydrophobic molecules will prefer being stuck in the solvent. The more hydrophilic molecules will be preferred to be bound to the paper, or whatever the solid support, whatever your stationary phase is. So let's just, so I think in the instructions, I think the first one we're going to do is the spinach in ether and acetone, okay? So we select that, and we just hit start. So basically, what we have here, you can see if I zoom in, let me see if I can zoom in here. You see on the bottom, this is sort of where, that doesn't look, can't really see that very much. Let's make it red, there we go. You see the spot here on the bottom? That's basically where you would spot your sample. So you would take your sample that and you would spot it on a dot there, and then mark it with a pencil, so you could see where everything started, right? And you'd spot it like 3 or 4 times at a dry, spot it some more. You want the spot to be small but really concentrated. You don't want a great big spot, because these things are going to spread out as they move up the paper. So if you have a great big spot at the bottom, it's going to be huge and very difficult to measure as it moves up. So because this is a computer animation, it'll be ideal, right? It'll just be perfect. So you have a really small, very concentrated spot. And then you mark where that spot is. Why would you mark it with a pencil? Anyone tell me why you would mark it with a pencil and not a pen?
The pen will smear.
As
The
pigment.
pen will smear faster.
The pen will smear in the solvent, that's right. What else?
The pen has pigment. It will change the color.
Exactly. Actually, that's one of the experiments you can do in the lab. It's really cool. You just take a black marker and you spot it and then put it in the
Fine, I just
chromatography paper, and it separates into like 4 different colors. You see all the different colors that are put into a black marker. There's brown, blue, and there's green. It's really pretty, actually, when you separate them all out. So you obviously do not want that. You don't want pigments from the pen screwing up your experiment. So a pencil is just graphite. It's just it's not really going to move very much. So, and if it does, it's going to all move together. It won't really interfere. So zoom back out, and we'll start one of these. So here's that's where the starting spot is. And so what we would do is we would drop it into the ether acetone mixture. Question: do you want your solvent covering the spot?
Wait, I'm bringing my homework to do in the car because I don't want to stay in the front long term doing nothing.
Okay.
Too bad.
And someone doesn't want to do their homework, or they really do want to do their homework. I don't know how that works. So question: do you want the spot with your samples on it to be put into the solvent or not?
yes, you want it so you can see how it reacts.
Yes? Anybody else?
Yes.
So if this is my spot, let me get my pen out here again. So this is my spot here. Where do I want the level of the solvent to be when I start my experiment? Do I want it to be above the spot or below the spot? So I've circled the spot. Do I want my level of the solvent to be here? Do I want it to be here? Or do I want it to be like right on the spot? So here's my 3. So do I want my level to be A, B, or C? What level of solvent do I want when I start my experiment?
B.
Okay,
C.
C, okay. So C, you're agreeing, or like yes, you're agreeing with B, or C, what number, letter C? Dang. Everyone all right there? Okay, so we have a vote for B, and we have a vote for C. Anybody else?
Vote for B.
B. Another one for B. So we have 3 votes for B and 1 for C. Anybody? A is not terribly popular. Okay. That might have been a vote for A, I'm not sure. So what do we think? A, B, C?
B.
Another one for B. Man, B's running away with it. Nobody else wants to weigh in? So who said C? Who said C? You're right. So you can take credit. Yeah, C. You want it to be below the spot, because if we put the salt, excuse me, if we put the level of the solvent up to B or A, it's going to dissolve our sample, and our sample's going to go into the solvent and not into the paper. So basically, we want it below the spot so that so as it rises, it mixes with the compounds that in our spot, and then the ones that are more soluble in the solvent are going to go with the solvent, and the ones that prefer to be bound to the paper will stay with the paper, and then it moves up. So if we put too much solvent in, basically we'll just dissolve it all back in the solvent, and it'll all just be stuck in the solvent again. So we wanted it C. We want it to stay below the spot. Right, so our solvent will be like there. So we'll put it up to there. And then as it moves up, it will take the spot and the compounds in the spot with it. If it's more soluble in the solvent, it will go with the solvent. So let's just start, see what happens. So we'll hit start. And you can see as the solvent moves up, the different compounds move up with it. So you can see the dark green moves the least, and then the lighter green yellow moves more, then the yellow, and then finally the orange last. So just click on show scale. First we'll click on the tube and then hit show scale. So now you see why, the other reason why we put a mark on what we call the origin. The origin is where we spotted our sample. So the origin is here, where we marked our sample. So we put a ruler there. We start 0 is the origin, is where the sample was spotted. And then we measure the distance the solvent moved. And then this is our solvent, what we call the solvent front. The solvent front is the distance that the solvent moved at any particular time. And so at the end of the experiment, the solvent front is the furthest distance that the solvent moved. And it's one of the reasons why, if we were actually doing this experiment in the lab, when you take the paper out of the chamber, you've got to mark the solvent front very quickly with a pencil, because the solvent is very hydrophobic. It's organic, and it will turn into vapor pretty quickly. So you got to mark it while it's still wet, while you can still see it. So we would take it out, we would mark it with a pencil, and so this distance from here to here, we call that D solvent. So that's the distance moved by the solvent, okay? And so what does that distance look like to you? So this is in millimeters. It doesn't really say what it is, but these are millimeters. So what would you say the distance of the solvent is?
6 millimeter.
6.2.
62.
Oh, yeah. I'm sorry. Yeah, the distance is actually centimeters. Each one of those marks is a millimeter. So I should have made that clearer. So yeah, so we would say it is
Up to the red color or the
no, up to the spot, up to this right there. So yeah, whoever said 6.2 is correct. That's centimeters, also known as 62 millimeters. It's the same. That's the same distance, right? Because centimeters are 10 to the minus 2 and millimeters are 10 to the minus 3. So it's a difference of 10. So there's 10 more millimeters. There's 10 millimeters in a centimeter. So you can do it either way. You can say, you can measure them in centimeters or millimeters. I really don't care. So yeah, so I would say that is, yeah, 6 point, it's right on it, right? We can even zoom in, give it a little bit, make it easier to see. So if we zoom in, sort of get a better look at it.
So what would the spot distance be?
Ah, excellent question. So yeah, so here's my, so if the distance, so the D solvent is 62 millimeters. Yeah, where do you measure the distance of the other things? Generally, it's something like, if it was a spot, these aren't really spots. Usually what we would do is try and find the middle of it. But for this, I think it's probably easiest just to look at the leading edge. However, you can look for the middle, or you can look for the leading edge. However you do it the same for every for every spot. For this particular experiment, I would probably use the leading edge just because if you look at these two, it's very difficult to see where the middle of the yellow spot is. It's hard to estimate where that would be because we really can't see all of it. A lot of it is blocked out by the green-yellow spot. So I would probably just use the leading edge. So for the yellow one, I would use this. And for the green, dark green, I would use that. Now remember, significant digits, you're going to have to estimate the last one. So for 62 millimeters, we would say 62.0, right? Because it's right on it, so we can pretty much make a really good estimation that that's 0.0. It's directly on 6.2 or 62. It's right on it. So our last digit is a pretty good estimate that it's 62. Now,
Second one, how much?
go ahead.
The second one, if you want to measure, how would you?
Let's do that. So let's even zoom in even more. Whoops. You can zoom in. This is the maximum you can zoom in. So what I would do is look really closely right there. So it's 60, 61, 61 and a little. So my D orange would be 61.1 or 2, something like that. You could make an argument for either one, 61.1 or 61.2. Let's say 61.1, just a little bit over.
So are these values supposed to go in the data table or?
Yes, indeedy. Yes, they are. So if my solvent distance is 62.0 and my distance for the orange is 61.1, and again, oop, I almost left out units. I could have been yelled at. So what is my RF, my retention factor for the orange? How would I calculate that?
You do 61.1 divided by 62.
Mm-hmm. Yep. 61.1 millimeters divided by 62 millimeters. What does that give me?
0.98986 or 985. 985.
985. Okay, yeah, 3 significant digits is good. What are the units? Just remember, a number without a unit is just a number. What do we put it?
Millimeters?
What are the units for retention factor?
Millimeter?
Nope.
Oh, sorry.
Now remember, sort of what I've been trying to show you since we started is when you're doing these sort of conversions, always keep the units in your conversion so you can see which ones cancel. Now the same is true here. So I've got 61.1 millimeters divided by 62.0 millimeters. So what are my units after I do all my math? So I've divided 61.
No unit because it's factor, correct?
No units, exactly. Very good. Yeah, so I've divided 61.1 by 62. I got my number. And I divided millimeters by millimeters. So they cancel. So retention factor has no units. It's one of those, every once in a while, we will come up with a measurement that is unitless. And generally, it's when we're comparing two things that have the same units in them. So if we're comparing millimeters to millimeters, that's going to be unitless. If we're comparing any sort of mass to mass, that's going to be unitless. It's a ratio. It's a ratio of 2 units, so it's going to be unitless. So we would report our retention factor would be 0.985. So our distances we put in our in our data table, and then we put for the retention factor, we report that, okay? So let's do the yellow one, just as, let's look at the yellow one. So so again, our distance solvent is the same. So all of these measurements we're going to be comparing to the same number. So the distance of the solvent stays the same every time. But what is our distance for the yellow? What would we say this distance is? So D yell. What's that distance?
Yeah.
44 millimeters.
Okay, so let's see, 41, 2, 3, 4, 44. Point anything?
0.2.
0.
All right, yeah. Some would say 0.2, some would say 44.0, some would say 44.1. That's your call. And you can see that that's why that last digit is an estimate. Some people would see 0, some people would see 1, some people would see 2, others would even say 0.3. Whatever you think it is. So because it's your estimate. It's nobody else's, it's your estimate. So let's say, okay, let's take the average of the two numbers I heard. Let's say it's 44.1. So what would my RF for yellow be? How am I going to calculate that?
44.1 divided by 62.
With your units. 4.1 millimeters divided by 62.0 millimeters. What does that give me?
0.711.
0.711. Okay. So because the orange compound had a higher RF, so this RF is higher than this one. Does that mean that the orange had a higher affinity for solvent or paper than the yellow? So what would its relative affinities be for would it have more affinity for the solvent and less for the paper, or more affinity for the paper and less for the solvent? Orange compared to yellow. What would you say their different affinities are? What could you tell me about those two different molecules by looking at their retention factors? That orange, man, could I have made that question any more confusing? So, orange versus yellow, which one has a higher affinity for solvent?
Orange.
Orange, yes, exactly. Because so it moved more with the solvent than the yellow one did. We would say that the yellow one was basically retained more by the paper than the orange one was. And so the yellow one has slightly more affinity for the paper than the orange. And the orange has slightly more affinity for the solvent than the orange. And that's what we're basing our retention factors and the relative movements are. Now, if we look at the green is way down here. So we say the green has more affinity for the paper or the solvent than the other spots. We would say the green is the highest affinity for which one? The mobile phase or the stationary phase? It's the lowest one of the four. It's moved the least.
Stationary?
Right. It has the highest affinity for the stationary phase because everybody else, all of the other things we can see, all the other pigments we can detect moved more than the green. So we can say that the green had the highest affinity for the stationary phase, in this case, the paper. So the other thing we can say is that the green pigment is chemically most like the paper and least like the solvent. And because the paper is hydrophilic, so this paper is hydrophilic, and the solvent is hydrophobic. So we can say that the green is the most hydrophilic of all the, because it moved the least. It is the highest affinity for the paper. And we can say that the orange at the top is the most hydrophobic. So we've learned something about these different pigments. Not only have we been able to separate them, we've learned something about their chemical characteristics, that the one that moves most with the solvent is most chemically like the solvent, and the one that moves least is most chemically like the paper. And so if the paper is hydrophilic, water-loving, and the solvent is hydrophobic or water-hating, whoever moves most with the solvent is the most hydrophobic. Okay, does that make sense to everybody?
Yes.
Good. Just one person understands me. It's what I'm looking for. All right, let's zoom back out. So what I basically want you to do is to run this experiment, and you can check your results, actually. If you show the chart, it shows you what it calculates as its retention factors. So your retention factor should be pretty close to those. But remember, I want to see your work. So I want to see the distances that you measured for each one of those. And so it tells you the differences. So the carotene moves the most. So the carotene would be the most hydrophobic. The anthocyanin basically doesn't move at all. We don't even see it move. The chlorophyll B is the dark one. It's the most hydrophilic of the four. And I think, we measured it around, 0.47 or something like that. So we were pretty close. And the xanthophyll was, I think we had 0.711. Excellent. So so run that experiment. And then I want you to pick, I think the second one was like either maple in autumn or winter or fall foliage, whatever you want to do. And do two different solvents. First, run it with the ether acetone and do all the calculations. And then run it with isopropyl alcohol and run all the calculations and see if you see any differences, okay? So let's go back and look at the, so here's the instructions. So it just runs through the types of chromatography, how it would work. So first we selected the spinach green extract. There's the spinach green extract in the ether acetone solvent. So you want to, put that in your data table. Spinach, what solvent it was, the different spot distances, the solvent distances, and give me the retention factors.
Do you want the retention factors for every color?
Yes. Yep. And then do either maple leaves in the fall or winter, or really you can do what anything different from spinach. You can do whichever ones you want. But what I want you to do is with both solvents. So once with isopropanol, and then once with ether acetone. So do both solvents and record those in your table.
For the same leaves, correct?
Yeah, if you would do just so pick whatever leaves you're going to do. Like you have three different. You have was it maple leaves in the summer, maple leaves in the fall, or a variety of fall winter leaves, all
Okay,
extracted. So pick one of them,
okay.
and
For
then
the,
save solvents. Yes.
okay, for the spot distance, I should mention like first one, 14 millimeter,
Well, these are
the
just
orange
examples.
one.
These are just examples.
Yeah, but I mean, I should mention what's color at this time just to show you how I am like understanding.
Yeah. So what are the different spots? And
For,
actually, you could make another column
I can,
for whatever the compound is. Actually, that's a really good point. You can make another column in here, put it between the spot distance and the solvent distance, and you could say which compound it is,
but
or the color, or just what the color is. You know, dark green, yellow,
for
green.
okay,
What it is.
for solving distance, it's gonna be the same, correct?
Mhm.
56, it will not change.
For each experiment, it'll be the same. Yeah. Now, I don't know when you do the different solvent, whether it's going to move the same distance or not.
Yeah. But I mean, like for here, for the first and second and third color, it's gonna be same.
Yes. So this will be 56.0.
Yeah, this is how.
This will be 56.0. And I think if there's four compounds, that'll be 56.0 as well. Yeah. But a different experiment, the solvent may move a different distance. I'm not sure.
Yeah.
Yeah.
Could
So,
you remind us what the spot distance is again?
oh, sure. Let's just go back. All right, let's spinach in ether. All right, so we'll let them move. As what I mentioned before, when we sort of do this in the lab, we make basically a circular spot, and then the circular spot will sort of spread out. But here, we just have one spot in a sort of a narrow piece of paper. So it sort of all moves up the sides. We don't really have a round spot, so it's kind of hard to measure where the middle of the spot is. So what I would suggest, oh right, we want to show the scale. We click on the tube and we show the scale. So here are our spots. So what I would do is probably measure the leading edge of the spot, because that we can see that best. And so like for the dark green here, for instance, I would measure it from right there. So like the leading edge of the spot. Let me clear that out. So I would I'm tracing the leading edge here. So I would measure it, right there. So 31, 2, 3, 4, somewhere like around 34 and a half, something like that, would be the spot distance. It looks like it's between 34 and 35, somewhere in there. So
For the spot,
wherever you see it.
So I was gonna say for the spot distance, that's when we input like for each color,
Yes.
the measurement for each color, and
Yep.
then the solvent distance is with the solvent distance for this be 62.0 millimeters.
Yep.
Okay. Okay, got it. Thank you.
For all four, it's going to be the solvent distance is exactly the same.
Yes.
So our retention factor should be all different.
Got it.
Yeah. So that our RF would be 34.5 divided by 62. And that gives us, what does that give us? It gives us like 0.556. Let's see what they 556. Let's see what they give us. So chart. Wow. Oh yeah. So what they're doing is they're measuring it from the middle. They're trying to estimate where the middle of the spot is. So their RF values are going to be slightly less than ours. Because where they're measuring from, let me sort of zoom in again. Where they're measuring from, they're trying to find the middle of that spot. So they're measuring around here. That's around the middle of the spot. So like around 30, 29 or 30. So if we use that, if we use 29 divided by 62, yeah, that gives you like 0.47. But I'm saying it's difficult for us to do that. That's where you should be measuring it from, but I'm saying it's kind of hard to do that, particularly with the yellow, because we don't really know where the middle of that spot is. Like in a perfect world, we would try and find the middle of the spot, but I'm saying it's difficult for these. So I would just use the leading edge. If you want to try and estimate the middle of the spot, go right ahead and mention in your results that that's what you tried to do. And your numbers should look closer to these. That's the proper way to do it. But I'm saying when the spots are too close together, it's really difficult to do that.
So we should look to the scale itself, not only the edge. Like,
Okay, what was your question?
like to take the measurement, I have to look to the end of the red color or the yellow in the top each one.
I'm suggesting that you use the leading edge as your measurement. Which color are you referring to?
Like, I saw there is yellow on the top of red and there is yellow on the top of green. So I have to look to the yellow color or the end of red.
Oh, red. Red we don't really see. We see the orange one at the top. So there's the orange one here at the top, and then there's this yellow one, and then the light green and the dark green. So there's 4. So I'm saying that yellow one is basically mixed with the yellow green one. So it's kind of hard to measure where the middle of each of those spots are. They are 2 different spots. So yeah, so measure the leading edge is probably the easiest thing to do. Erica, you had a question.
Yeah, I think like a few of us are kind of confused in terms of the data table and like yeah, like if you could just go through like maybe just one example like below the because we're not, or me personally, I'm not sure if the one that's already written on top is just an example.
Just an example, yes.
Okay.
It's just an example. Yeah, don't use those numbers. These are just examples. Those aren't for you. Those are just examples of something you would write in there. So what you should have numbers with 3 significant digits, and then your RF calculated here. And like I said, if you want to put another, you can either put the spot distance and the color, or you can put another column in here and just have, spot color. That's fine. But it would be a good idea to have something with the color in there. And so and also you should have 4 spots, not 3, because there's 4 spots in the spinach extract. The one we just did with spinach extract with ether and acetone had 4 spots. And you can do them in any order you want. The one that moved the most could be first, or the one that moved least could be first, whichever. But yeah, there should be some indication of what colors they are.
Thank you.
Yeah.
So, Professor, I
Yes.
have a question.
Mm-hmm.
For the example that we had, like the orange, the spot distance was 61.1 millimeters, correct?
I think so, something like that. Yeah.
Okay. All right. Thank you.
Yeah. So we put 61.1 here, and then since the millimeters are given here, you don't really need to put them in here again. It's another confusing thing. It's kind of stupid of me. And then this was what, 72 or 62, 62.0. So then we would give our RF here. But yeah, I would like to have the color in there. That's a good point. So is everyone else clear? So the rest of it, I want you to do on your own. So watch the videos. Pick one of the, let me go back. Pick one of the other leaves. It can be whichever one you want. So either pick the maple, one of the two maples or the fall foliage, whichever one you want. Do it with both solvents and then answer the post-lab questions.
For the spinach, you know how there was a red but it didn't really show up on the scale? What would we put for the spot distance? Would we just put
That doesn't show up. There's nothing.
so nothing?
It's
Okay.
not available. Yeah, I wouldn't even include this because we can't see it. So if we didn't see it, we can't measure it. So I wouldn't even include it.
Okay.
Now there's one of two reasons that would have happened. Either A, it didn't move at all. And so it's still at but basically it just means we can't see it. So either it's probably just too dilute, like maybe that extract that we made for this experiment was too dilute and there wasn't enough anthocyanin there for us to detect it. That's all. We could like take this paper after we dried it, we could spray it with something that detects anthocyanin. We could do that, and then maybe it would show up. But we can't see it here, so there's no point including it. I mean, if you can't see it, you can't measure it. So I would not include it. Now the anthocyanins, that's where the red color comes from. That will show up in the fall and winter foliage, right? When the leaves turn that bright red color. Then you'll see it. But in the summer, there's not much of it there. So that's why it's undetectable. In the fall, you're going to see a lot more of it. So any other questions?
I have a question from the post lab.
Okay.
Question number 3. What do you mean about is the retention factor is intrinsic or extrinsic?
Yes. Right. So when you measure the RF of each of these things, basically an intrinsic property is unique to that particular molecule, and it is independent of how much of that molecule is present. So if I had, let's say if I had 10 milligrams of anthocyanin or 12 milligrams of anthocyanin, are they going to move the same distance on the paper?
No.
No? How come? So would I get 2 spots? Would I get 2 red spots? If I had, here's my 2 chromatograms. That's what we call a separation, a chromatogram. So once we take it out, we call it a chromatogram. So here are my 2 chromatograms. So on one, I've spotted 10 milligrams of anthocyanin, and on the other, I've spotted 12. So here's my red spot for my 10 milligrams. So in the 12 milligrams, am I just going to get a slightly darker spot, or am I going to see a second spot either higher or lower? What do you think? Am I going to see 2 spots there, Or am I just going to see a darker spot in the same place? Anyone can answer. So the only difference between these two chromatograms is on one, I've spotted slightly more sample. So I have slightly more sample in one. So is that going to lead to additional spots or a slightly darker spot in the same place? Basically, it's one or the other. Which one do you think?
Slightly darker.
Okay, why do you think?
Maybe because there's just
That's the explain part.
okay. Probably like just because there's more in that. There's just more in that.
Because why?
There's just more in that one spot, so it make it.
Okay. Yeah, because basically, so think about what you're basically saying is that it's the same compound, right? It has the same chemical character. So this amount and this amount both have exactly the same chemical characteristics. And it's the chemical characteristics of that compound that are responsible for how far it moves up the paper. So it's the actual chemistry of that compound that leads to its RF, not the amount. And so if you have a property of a compound that's not related to its amount, is it intrinsic or is it extrinsic?
If it's related to the compound,
And not the amount of it.
it's intrinsic.
Just like density, just like the experiment we did last week. The density is independent of how much stuff you have because it's mass divided by volume. And so the more mass we have, so if mass goes up, volume goes up too. And the ratio stays the same. If the mass goes down, the volume goes down, and the ratio stays the same. Just like here, if we spot twice as much material, basically when it separates, we'll just get a spot that's twice as big. Now, what may happen is it may spread out a lot more. And so we may not see it, we may not get an accurate determination of its retention factor, but it's basically going to go to the same place. So like my small amount may give me a spot like this, and the big amount may give me a spot like this. But basically, if we looked at the middle, it's going to be the same. Just one will just be bigger than the other one. So my retention factor stays constant because it's based on the internal properties of that molecule, not its external properties like amount. Okay, so it's an intrinsic property. And that's how we can separate these things. Great question.
Professor, can you repeat it again? So you said it if it's different amount but same chemical characteristic, it's gonna be extrinsic.
Intrinsic. If I spot two different amounts of the same thing and they go to the same place, they basically have the same chemical characteristics.
Okay.
It's independent of the amount. And if it's independent of the amount, it's an intrinsic property. Like the color of gold. Doesn't matter how much gold I have, it's going to be the same color. Its mass or its volume is an extrinsic property. That depends on the amount. If I have twice as much gold, the mass is twice as much. So that's not an intrinsic property.
So in that case, the spot will be higher or darker? This is what I'm
Darker.
darker.
Darker. But yeah, this point over here was that it may be more spread out. If I spot like way too much of something, I may get like a big, ugly spot because there's just too much stuff there. But the retention factor should roughly be the same. So it won't be as pretty a spot.
So no matter how much I put milligram, it's gonna be the same RF.
Should be. Yeah, I mean, eventually you'll spot so much that, you know, you'll just get this big smear. And eventually this will break down and you'll just get this big smear of stuff because there's just too much there. You will basically exceed the capacity of the paper to bind it. Like if you have way more molecules, way more more stuff than the paper can actually hold, yeah, then your experiment's not going to work. But as long as you're within the capacity of the paper to hold on to the molecules, your RF will be the same. That's why I picked something that's like, you know, 20% more rather than 10 times more.
Okay, so I have a question. When RF it's the same, it means it's intrinsic. When RF it change, it means extrinsic.
I didn't get the second part of that.
So I said, if RF it's the same, it means it is intrinsic. If RF it change, that's mean it's extrinsic.
No, it just, if RF is different, that means those two spots have different intrinsic properties. Because RF is an intrinsic property of the molecules. So if I have two molecules with different RFs, it means they're different chemically. Intrinsically, they're different.
Okay. And if RF it's same, that's mean it's extrinsic. Like to answer this question, if I put a 12 and I put 10 milligram and I have the same RF as you said, gonna be extrinsic, correct?
No.
Oh.
Intrinsic.
Okay.
Basically what it's asking is for each of those individual molecules, can you identify them based on their retention factor? And the answer is yes, you can, because they're all different. Now, if I was to say I have 5 different metals, can you identify them based on their mass? The answer is no, I can't. What if they're all the same mass? What if I have like 10-gram samples of 5 different metals? Could you be able to identify them based on their mass? No, you couldn't. But you could identify them based on their density, or you could identify them based on their color, maybe, although a lot of metals are the same color. But yeah, you could measure them based on, you could differentiate them based on something other than their mass. That's not an intrinsic property. An intrinsic property is something that is unique to the molecule. That's all it means. Is the retention factor unique for each molecule? Now, you will notice, to make it a little more confusing, you will notice when you pick a different solvent system, your retention factors will be different. That does not mean that there's no longer an intrinsic property. It means that the RF is dependent on 3 things. It's dependent on the chemical properties of the molecule, the chemical properties of the solvent or the mobile phase, and the chemical properties of the stationary phase, or in this case, the paper. If I change the solvent, I'm changing the retention factor. If I change the stationary phase, if I change the paper to like silica gel or something, well, it's different. The retention factor is going to be different. but the retention factors are still going to be unique to each of those molecules.
Okay.
But they're dependent on my choice of solvent and stationary phase. Yeah, do the experiments. Get your results. If you have questions about it, yeah, just drop me a note. And I'll be having office hours tomorrow at 10:30. You can drop in there too.
When is the due for this lab?
When is it due? A week from today.
Okay, good.
Yeah, I just posted it. All the labs and recitations are due a week from the day we do them together.
I have a
Right.
question.
Sure.
About the recitation that's due. If we do it on paper, do you want it on? Do you want that in pen as well?
It's pen just generally is more readable, excuse me, than pencil. When you take a picture of it, it's much easier to read pen than it is pencil. Pencil is just it's harder to read. You know what I mean? It rubs off, and yeah, I'd prefer pen just so I can see it. But if you write like in a really dark pencil and it's legible, fine. But if it's not legible, I will write a note on it saying it is not legible. So yeah, you're free to do whatever you like, but yeah, that's what I would prefer because I can read it easier. Maybe you've got some sort of super pencil that's really good. But yeah, I don't like writing in pencil myself. Like I can barely read my own handwriting as it is. Pencil just makes it worse.
Okay, Professor, for the calculation, for the measurement, is it okay, like, if there is, like, not accurate, like, every student has different, like,
Yeah, it's whatever, yeah.
point one
The
for
first
point,
two digits should be the same for everybody. Like you should be, we go back.
like, if I say 61.1 and other classmates say 61.3, it's...
Yeah, that's fine. Yeah, because your RFs are going to be pretty similar. So if someone calculates an RF as like 0.455 and you calculate it as 0.453, that's close enough. That's really, because you can see there's a lot of error here. These spots, like especially if we did this, when we do this in the lab, these spots spread out.
Yeah.
And so it's really hard to get a super precise measure of the distance. So yeah, you will not lose points. I mean, because it's your measurement. How can I take points off if it's your measurement? Where I would is if you claim that the solvent front was 72 millimeters rather than 62. Well, that's a problem. But if you think it's 61.8 rather than 62, well, that's what you see. I can't tell you what you see. That's fine. It's one of the many reasons we like people to work in pairs in the lab, because one person will say, what do you measure it at, and then the other person will measure it, and then you take the average. That's generally more accurate. So yeah, whatever you see it as, that's fine. And you should be able to get it within, plus or minus like 0.3 millimeters. It should be pretty close to that. But remember, the RF values that are given here are going to be less than the ones you calculate, because they are attempting to find the center of those spots. And I'm saying that that's too difficult to do for some of these. When they're too close together, it's hard to do. If you want to try and do that, totally fine. So anything else before we call it an afternoon?
There is also error analysis questions.
Uh-huh.
Question
Those-
number 3.
Those are for you to think about, but I can give you a hint, but I'm not going to give you the answer. So let's see. Okay, which one?
Number 3.
Okay. Okay.
Imagine a researcher left the mobile face setting.
Uncapped. Mm-hmm. Yep. Yeah, just what do you think?
Change outcome of
Yeah, I just want to know what you think. It's like there's no right or wrong answer here. So yeah, if you still think about it. So that's another reason why we put the top on the while we're doing the chromatography. We put a big top on it so that the solvent doesn't evaporate. Because basically we want the solvent to stay the same as it's moving. If we have a mixture of like ether and acetone, the ether is going to evaporate faster than the acetone. So at the end of it, we'll have a difference. So if the ether evaporates as the experiment is going, we'll have a different solvent at the beginning than we have at the end. So that will affect things. So tell me how you think that would affect things.
Okay, could you explain number 2? What do you mean about stop the development of the paper? What do you mean about development of paper?
Okay.